Everybody is awake? Yeah. So welcome to my presentation about state machines. So no, the joke is that when I presented the last time at ROS-Con in Japan, I had this slide on my presentation that said what behavior trees do better than state machine, and I got the feedback that was Kate maybe said, "Oh, you should remove this slide; it will upset the state machine guys." So and of course what I did was to leave the slide there. Okay, so BehaviorTrees CPP. So usually when I give this presentation, I introduce what the concept is, and I have a few slides about it. But today, for the first time, I want to focus most on the tooling around it and why I believe this tooling is valuable for the industry. So a little bit of history. This project was originally developed at IIT before 2018. It was a very simple library. Then in 2018, as a cascade funding project from Ron Moses, I started basically forking this library and creating my own. And since then, I've been developing it and maintaining it. And nowadays, it is increasingly popular in robotics. I've seen it used in underwater robots, drones, quadruped robots, of course, robotic arms, autonomous navigation. So there are many domains that are adopting this as a standard. And for the few of you that maybe don't know, this originated in the gaming industry. So I would say that this library is probably among the first that really took this concept and made it available to the robotic community, trying to understand what robots need to do differently. It was made popular mostly thanks to Nav2 that adopted it as a substitute of plugins to give more configurability about the recovery behaviors. And the way it is done, and I think that this was mentioned 10 minutes ago, the way it's done is a pure C++ library with a thin ROS wrapper around it so that there's a good separation of concerns there and separation between what the middleware is and what the core library is. So what is the problem we are trying to solve here? Why do we need a library like this? Because usually in robotics, historically, we were always focusing about what the robot does and in terms of skills. Can the robot navigate autonomously? Can the robot do path planning and motion planning? But now, as an industry that is more mature, now we have other questions. It is how do we assemble all the skills together into a mission, into a task planner that can solve a certain job. So there is a new shift because basically those problems, those skills exist already. Of course, there is still more work that needs to be done, but they are there. And what we want to do is to build something that is reusable, modular, and composable. So this is basically what we want to do. And usually when we talk about this, we talk about this task planner. And here we need to be very specific because we're talking about explicit task planning. There is now a new trend about a symbolic planning that is very promising. Here we are talking about more maybe old-fashioned or mature, if you prefer this word, approach to something that we can program entirely, and also to give us the confidence that we can understand what's going on. So I'm going to use the word task planner, but you can call this coordinator or orchestrator. It's really about having a single component that has some knowledge about the system and the mission and can interact with all the other components that are more service-oriented. So what are behavior trees? The way I like to look at them is an alternative to hierarchical state machine, but also as a domain-specific language. And I think this focus is not very common. Very few people draw that similarity with the domain-specific language, but I think it is because it's really a way to express your intent with a set of instructions that are specifically tailored to give you expressiveness in that domain. And also it's something that you can extend. So as I said, we are talking about explicit task planners, and Also, I'm not here to sell you the idea that this is the solution to all your problems. It's not a silver bullet, but for sure, it's something that I keep on receiving as a feedback. They are much better than the alternatives they had before. So I know that this is something that helps people create richer application, more complex and scalable applications. Then if you ask me if this is the solution to all our problems in robotics, probably the answer is not. And that's why I'm also keeping myself an eye on symbolic planning as something that potentially can be interesting in the future. So finite state machine and behavior trees. To understand, to grab the difference between the two, let's start saying that probably state machines are more intuitive as a user. We have a mental model of them as that is more familiar. Also, if we want to describe them in terms of, I'm going to use this word meta model, this fancy word. If we want to describe what they do, how they work, we just have a simple concept that is the transition. The problem they have is that usually they are harder to scale into big behaviors, and it's not clear how to model concurrency. Even if recently there has been some attempt with the SMAC that tried to model concurrent behaviors. And their graphical representation is usually doesn't scale well. So people that use the graphical representation of state machine probably know that they spend 2/3 of their time moving boxes so that the line don't cross too much each other, instead of reasoning about the real application. So doing manual layout. In behavior trees, instead, we have a richer grammar. We don't talk just about transitions. We have a concept like sequence, fallback, or decorator that by themselves express a higher level abstraction. So it has an implicit meaning that make our graphical representation easier. And most importantly, the graphical representation itself has some meaning. What I mean is that, in a state machine, the position of your box doesn't really affect the behavior. Instead, in behavior trees, you usually have this ordered list of children, and the order from left to right also represent as a semantic meaning. So the way they are ordered on the screen affect the order of execution, and this also means that you can read them from top to bottom and to left to right as text. So this makes them more human readable. Then in particular about this implementation that I did, there is a lot of inspiration from model-driven development. So a lot of the good concept I learned about this has been applied to the library in terms of separation of concerns and expressing to the user a sufficient amount of information, that is the model, to allow him or her to understand what's going on without inspecting the code. Then it is very focused on C++, but there is an XML tiny language that is what we use to express the tree. So the node of the tree is implemented in C++, but the tree itself is an XML scripting. And this is really powerful because it allows us to do a lot of things that otherwise would be impossible if we use code generation or just hard code our tree structure into C++ code. We can use it in an editor, so we can, otherwise it would be impossible. We can send very easily over the wire the structure of the tree for tooling, and we're going to talk about these tools later. So that is really powerful. And also, I had experience with another library like PyTrees that is a great library, but the problem I observed there is that it was this mix. Everything was mixed together, implementation and definition of the tree. So understanding the tree was really hard and required inspecting a lot of different files. And And then there is this new concept that was introduced with version 4 in Japan at ROS-I. There is this concept of pre- and post-condition that, as far as I know, is kind of novel. So there's not much literature about it, mostly because I took inspiration from some Unreal Engine implementation and then create my own grammar. So you won't find any literature. It's kind of novel, and I think that it really can help people scale and express more their intent with less boxes, so in a more concise way. Something I'd like to talk about today is the tooling. So GR2 is the graphical user interface. I like to call it IDE. Could be kind of an overstatement, but I think it's good because it's really a way not just to edit and visualize behavior trees, but also can be used during the entire life cycle and development of your system. So GR2 allows you to visualize and edit behavior trees. It has a new multi-file architecture that allows you to split very large behaviors on different XML files and compose them into a project. Also, you can attach to a runtime behavior tree executor, something that is running, for example, on your robot, and visualize in real time the tree that is being executed, the current state, which boxes have been ticked, and return a certain value, or the internal value of the blackboard. There is, for those who don't know, the internal data flow mechanism in behavior trees. Then there is another module that is instead focused on log visualization. So you can load a log that was recorded previously and replay all the transition that happened. Or you have finally an interface that is like a debugging, interactive debugging, think GDB interface where you can basically insert a breakpoint and interact with the tree at runtime. So this is the area that I think is particularly important in this library, the debuggability and observability framework it offers. Why I believe that is valuable. If you think about the general architecture we have in robotics, we can see mostly, very, very roughly, 3 layers. The hardware absolute layer, we talk about that today with the ROS control. The skills or functionality that could be move it or could be nav2 or all the other perception software you have. And then there is what we are talking about, this last layer on top, the more abstract layer that is about the task planning. And usually, especially for products, there's a lot of interest about understanding the metrics of your robot. How many actions happened in a certain day? How many hours you have been doing? Have the robot been doing a certain action? How many failures did we have, and were we able to recover? So there are a lot of statistics and metrics related to that high-level mission and state that we have in the robot. So, and because of the fact that it's the more abstract layer, is also where sometimes give us more information at a high level about what's going on. So having a framework that allows us to monitor this is at a lot of value when we have a fleet of robots or just a single one and we want to know what happened maybe with some logs. The way this is implemented is basically with what is called in programming the observer pattern. So every time there is a state transition in one of the nodes, there's a kind of signal slot to publish subscribe architecture that will invoke different 0 to n attached loggers, and these loggers can maybe save the information on a file on a database, or publish that information to an outside process, or just collect statistics about it. For example, the ability to collect statistics allow us to create a unit test in a non-intrusive way, because usually if I want to implement a unit test of a behavior tree, what I want to check in my assert command is, okay, was this recovery behavior invoked? How many times? What did it return? with an observer, I can collect that information in a non-intrusive way. So this also help us creating unit tests and integration tests. And something else is also allow me to do fault and code injection. So this means that, and I'm going to show you more about this, but this means that I can basically force a certain node to return the value I want, not the one it wants. And for example, this allows me to say, okay, I want to see what would happen if this action fails, this localization action fails, because I want to see how the recovery behavior acts. So I can force that fault and experiment and see how this other branch that otherwise would not be taken is actually taken. So this is an example of how the log visualization works. So there is the central area where, based on the color, you can see the state in a certain amount of time. So the orange one are the running nodes. The green and the red are for success or failure. You can see the entire list of events on the right of the transitions. Actually, I'm experimenting with a client I cannot mention. They have 500 megabytes logs, 2,000 nodes trees. I don't know how that happened. And probably transition for a few hours. So logs that are like 8 and 9 hours long. So this is all supported. There was a lot of work in terms of scalability. Then you can visualize the different trees individually or all at once. And you can also create statistics. So for example, you can create, you can ask, okay, how many times this node was invoked? For how long? How many times it returned success or failure? So you can build statistics out of this. And then there's this real-time debugging and result injection. I'm saying result instead of fault because you can also inject a success, where, for example, you can, well, first of all, you connect remotely with an inter-process communication that is not ROS to your running behavior tree. Then you can visualize on the right side, you can visualize the blackboard, and you can double-clicking, you can insert a breakpoint. And the breakpoint could be interactive. So for example, when you reach this block and ask me what to do, if continue, force a failure, or force a success, or could be just replace this node with something, with a dummy, that always return success. So you can also do something like hardware in the loop simulation. So say, okay, my robot doesn't have a camera, so substitute this camera node with a dummy one that always returns success. So I don't know how much time I've left. This maybe was a fast presentation, so a lot of time for questions. Summary already. So the BehaviorTrees CPP is this completely open source library. It's an MIT license. You can use it. I know that some of you use it. I think it's very stable, even if every time I was joking during the lunch that every time I say, this is the good one. This is the one that really works. There's always the day after somebody submitting a critical bug. But anyway, I think it's stable enough, and actually I don't plan to add big features in the future. So at least it's feature complete. GroupShoe, it is already available. It's free for academia and non-commercial use. You should give it a try. The editor is 100% free, so it is definitely a very good tool you can use to edit and visualize your XML files. And as I said, what I think that is very valuable, in particular for an industrial user, is this ability to interact with this layer of your robot and have observability of what's going on, what the problems are, why you felt into a certain behavior that you did not expect. So I think this ability to debug your robot is very valuable, and you should try. And you can also extend it with your own custom-made interface. Very fast shout out, since many of you are in the business or in the industry of robot manipulators, check Movie Studio. They have also a fantastic behavior tree editor, and much, much, much more. So if you're working with the robotic arms, you should definitely check this out. It has also very advanced motion planning, perception, visualization, and behavior trees. So they have that and a lot more. So check it out. Thanks.
Thank you, David. Okay, we already have one question.
Thank you for your presentation. I have actually a question regarding the new features or feature you presented. I was playing somehow with your behavior trees, but what I was missing actually was to use the GRUT and to insert, as you mentioned, sort of breakpoints. So, for example, I wanted to make some kind of loop or whatever node to make a failure or whatever, so the code had to be recompiled. Mm-hmm. So I would like to ask if you think that, for example, I can play with the behavior trees on the fly. I mean, for example, let me see. I can create my application and start simulation, and I can, let me see, force the behavior or particular node. So okay, I have this one. So what happened with the robot on the fly? So
exactly, that's exactly what it does.
So this is wonderful. Yeah.
Okay, thanks.
Yeah, thank you. But the other question, do you think that since the Move-It has this interface, Python interface, do you think that will be also useful to use Python as a, for example, as a, I don't know.
So there is some brainstorming with some users about having a node invoking a Python script. So there is some proof of concept done, and it's technically possible. The problem is the blackboard type. So the C++ version uses strongly typed C++ classes. If you have a Python wrapper, you need to deal with that. It is possible, but it's not obvious how to do that technically. But I'm happy to explore that if there is, in the future.
Yeah, thank you for the contribution as well. So just a general question. If you short can explain when to use a sequence, a thought and behavior trees. So when would you use what, or are you all into behavior trees now?
I'm not sure what you mean by sequence.
So you start introducing these two
yes.
concepts. So
that was a behavior tree. So the one on the left was a state machine.
Yeah. Okay. So state machine.
Okay. State machine.
Kind of program in sequence.
Okay. Sorry.
Behavior trees.
So when to use state machines? Right. I would say that a state machine makes sense with smaller when what you are modeling is smaller in size, because the real problem is the scaling. There's nothing wrong intrinsically with state machine. They're perfectly fine. I've used them in many cases. The real difference is your ability to scale it. If you have a very large behavior and you want to compose them, a simple behavior into a bigger one. So you might have a tree that expresses pick and place, and then you insert this subtree into a bigger tree that does morphing. Technically, you can do the same with the hierarchical state machine, absolutely. It's really a problem of being able to fit this into your brain. There's a point where when you reach a certain size where you don't understand what you have just written anymore. And you get to the point also with behavior trees, but with bigger behaviors.
Okay, thank you. And if there are any questions, we can still take one short one.
Yeah.
Okay.
I have a really short one. It's just be yes or no, and I can always talk to you later. But I'm curious how many people are working with you as far as multi-robot coordinated tasks with behavior trees?
Yeah, I'm in. Okay, so the question is not yes or no. So yeah, yes, I am in contact. Yeah, I'm in contact with companies in the drone industry that are using behavior tree in the context of fleet. But my recommendation is do the individual autonomy of the robot with behavior tree, but don't do fleet management with behavior trees, because as a domain-specific language, this is not the domain where it is more expressive. So my suggestion is to have a more scheduling, a sequencer, a different way to design your fleet management. But then for the individual autonomy of your autonomous UAV, vehicle or autonomous drone, then you use behavior trees.
Thank you.
Thank you, David, again.